Work Energy Power, Part 2 by Anandovsky. We know that work is done when a force is applied to an object. Two types of forces can act on an object: constant force and variable force. The work done by a constant force refers to a force that always maintains the same magnitude and direction, while a variable force is a force that changes in either magnitude or direction over time or with position, meaning it is not consistent throughout the interaction with an object. The formula for work done by a constant force is F into d into cos theta, and formula for work done by a variable force is integral x1 to x2, fx dx. You can check out the examples given and understand the formula for work done by these forces. We have already seen that energy is the ability to do work. It comes in different forms like motion, kinetic energy, and stored energy, which is potential energy. Energy also comes in other forms like heat, etc. Here we are discussing kinetic energy, which is the energy of motion. If something is moving, it has kinetic energy. The formula for kinetic energy is half mv squared. The work energy theorem states that the net work done on an object is equal to the change in its kinetic energy. Maybe you have not understood work energy theorem. Let's simplify it. Alright. The work energy theorem states that the work done on an object is equal to the change in its kinetic energy, mathematically. W equals delta Ke equals Ke final minus Ke initial, where delta Ke equals change in its kinetic energy. You can see the example and understand the theorem. We have seen that power is how fast work is done or how quickly energy is transferred. The formula for is work done divided by time taken. Instantaneous power is power at a specific moment. Instead of total work over time, it depends on force and velocity at that instant, so we can say power equals force into velocity. When we consider theta as the angle between the force and velocity, the formula becomes power equals force into velocity cos theta. A car's engine power changes as it speeds up or slows down is an example for instantaneous power. You can check out the example problem and understand it. We have seen kinetic energy. Now let's look at potential energy. Potential energy is stored energy due to an object's position or state. It can be released and converted into kinetic energy. Here we are discussing two types of potential energy: gravitational potential energy and elastic potential energy. Gravitational potential energy is energy stored in an object due to its height above the ground. The higher the object, the more energy it has. The formula for gravitational potential energy is mgh. Elastic potential energy is energy stored when something is stretched or compressed, like a spring or rubber band. The formula for elastic potential energy is half kx squared. Potential energy of a spring is a perfect example of elastic potential energy. You can check out the example to understand how the formula is used. Forces in physics are often classified as conservative or non-conservative based on how they affect energy in a system. Conservative forces, like gravity, store energy and do not depend on the path taken, while non-conservative forces, like friction, dissipate energy and depend on the path. Let us look into motion in a vertical circle. Motion in a vertical circle is when an object moves in a circular path while being affected by gravity, causing its speed and tension to change at different points. Example is a roller coaster going around a loop. Let us think about some simple questions that can be asked about motion in a vertical circle. A basic concept question can be: what is vertical circular motion? Why does an object move faster at the bottom of a vertical circle than at the top? Now the answer can be found using some formulas. First, let us look at a formula to find net force in circular motion, which is also the formula for centripetal force. F net equals F centripetal equals mv squared divided by r. The example problem will tell you how to use the formula to find the answer. Another formula is to find the minimum speed required at the top to complete the circular motion. To find the net force at the top and bottom and also to find the minimum speed required to complete the loop, we use formulas like T bottom minus mg equals mv squared bottom by r. T top plus mg equals mv squared top by r. and V minimum equals square root of gr. T bottom is the tension in the string, mg is weight that is acting downward, and mv squared by r is the centripetal force. Also T top is the tension in the string when the object is at the highest point of the circular path. The example problem will tell you how to solve it using the formula. A collision is when two objects come into contact and exert forces on each other for a short time. Collision can be elastic or inelastic. Elastic collision is when objects bounce off each other without losing energy, like two billiard balls colliding. Inelastic collision is when objects stick together or deform, losing some energy as heat or sound, like a clay ball hitting the floor and not bouncing. Perfectly inelastic collision is the most extreme case of inelastic collision, where objects stick together completely after impact. One-dimensional collision. One-dimensional collision happens when objects move along a straight line before and after collision. Example: two billiard balls colliding head-on in a straight line. A formula in one-dimensional elastic collision is shown, you can refer it to do problems. Two-dimensional collision. Two-dimensional collision happens when objects move in different directions before and after the collision, not just in a straight line. Example: billiard balls colliding at an angle. A formula in two-dimensional elastic collision is shown where the kinetic energy is also conserved. Thank you for watching.